Okay,
It is kind of
so let's chit chat about what I want. So on page 2, here's definitely what I want. So understand that you have these concentric pulleys and you tied strings to them. So, and this is going to be important when you get to the last question. Now, on the last question, we're going to go through it. You're going to have a question like that on the test tomorrow. It is not, I'm not going to make you go through all of the algebra, okay? I'm just going to expect you to understand, hey, what's the process to get the problem started, okay? So here's the basic idea. So on that small pulley, you had a 20-gram mass hanging down, okay? So if you look at if you just isolate the forces that are acting on this, you've got gravity pulling down, and you've got some tension acting upwards. Now, this is going to be important when you get to the last question. You've got gravity pulling it down and tension acting up. Clearly, which force is bigger?
Gravity.
Gravity, because that's the direction that it accelerates, okay? If I hook this up, there's going to be a problem like that last problem where you actually have one going up and one going down. If that's the case, then if it goes up, the tension is bigger than the gravitational force. If it goes down, the gravitational force is bigger than the tension. So that tension is what's making that disc spin. Because if you just cut that string, then there is no tension, the pulley doesn't begin to accelerate. Okay, so the only way that accelerates is because there's some tension in that string. So what I want here, okay, where you've got your average acceleration, tension, torque, angular acceleration, moment of inertia, okay? On that average acceleration, if you just want to take your average time and do one calculation, you can. Just show me, hey, main thing I'm looking for there is that do you understand that you took 2 times the distance that it fell, divide that by t squared to get your linear acceleration. That's the only thing I'm really looking for in that box, is that you understand this is how we get our linear acceleration, which should be a positive value. God, don't make displacement negative. Now, to get your tension, okay, and understand where this comes from, because this is going to play out in that last problem and on the test tomorrow. How you're going to get that tension is that you realize that net force equals the difference between 2 things. The gravitational force pulling down and the tension. And we subtract M1 minus G minus the tension because the gravitational force is bigger than the tension. If the tension was bigger, I'd take tension minus M1G. Okay? That's the story. Now, that's going to equal your net force, which is going to be M1A. So, if I move this tension over here, do a little bit of hocus pocus, and move that M1A over there, then I've got M1G minus M1A equals the tension. You factor out that M1, you've got G minus A times M1 equals your tension, okay? Understand where this comes from. Just don't blindly write this down and go, oh, it's a miracle. No, okay? Understand the origins of these equations. So like when I did it, like that first tension that I had was about 0.2, okay? Ballpark, okay? Now, to get your torque. So there has to be some torque acting on this thing or otherwise it would never spin, okay? Now, conveniently on these trials, you only have one torque because you only have one string acting on it. So the torque is going to equal that tension times the radius. So you just found the tension. I gave you the radius, 0.018 meters, because it isn't acting on the outside. It's only acting on that inner circle. So my torque was like 10 to the minus third. Okay? It's going to be a pretty small number. Now, your angular acceleration, you have A equals R fish. So at this point, you know the linear acceleration of the following object. You know what A is. You know the radius, find your alpha. Divide that over. So I got an angular acceleration around 40 radians per second squared. Okay? So then, the last thing you need is your moment of inertia. So understand, the formulas for moment of inertia are basically mathematical in their derivation. This, and you can't directly measure it. You cannot go, hey, Burkant, give me the moment of inertia sensors. We don't have them, okay? They're important, we just can't directly measure it. So what you're going to do on that one, and remember that torque equals two things. It equals I alpha, or I fish, and it equals force times radius. So at this point, you have found the torque. At this point, you have found the angular acceleration. Boom, you solve for moment of inertia. So typically, your moments of inertia are in the big 10 to the negative fifths, like 8, 9, something like that, 10 to the negative fifths, or the small 10 to the negative fourths, like 1 or 2 times 10 to the negative fourth. Yeah, Sean?
You just had one trial in the 20 grams with the large buoy. Got a 1.49 times 10 to the negative fifth.
Oh, that's cool. Yeah. No, you're good. You're good. Okay. So, on the analysis part, so you have to figure out the theoretical value, which is this is a huge if. It should be around 7 and some change times 10 to the negative fifth kilograms meters squared. Okay? Because it's just 1/2 mR squared, you treat it as a solid disk. Okay? So what should happen is that because of the fact that all you're doing is you're basically running 4 trials to try and calculate the moment of the inertia of the disk, you should get the same, and if all was well and right with the world, you would get the same moment of inertia every time. Okay? So, and again, make sure in the big bold letters I said, calculate the experimental for each, show the calculations. So you're going to take your theoretical value, which is 7 and some change, times 10 to the negative fifth, minus what you got for trial 1, divided by times 10 to the negative fifth, times 100. Yes. Now here's the problem. Because you're dividing by 10 to the negative fifth, okay, which is a really small number, so if you're off by a little, that tends to get magnified in terms of your experimental error. Now, you got what?
1.49 times 10 to the negative fifth.
No, your experimental error.
Oh.
Experimental error.
80. Okay, I got 80.5 after recalculating it.
Okay, but the first time you had like
414.
400 and some odd. Yeah, that's bad.
Yeah,
So,
Me and Cohen's data
Put the
had the
gap in that name.
largest
Okay,
discrepancy
so I
between
did
which one
screw
was
up
better
when I
and
got
worse.
that number.
yeah.
I got like 5% for the first one.
Oh, that's nice.
Yeah, and then 80% for the other one.
Oh, yeah. See, here, the toughest one is always the one where you have that biggest pulley,
Yeah.
the 20 grams, because that has the biggest acceleration. So that's the toughest one to time precisely. So, okay, cool with that
I
part
was
of
too
it.
good with the 10-gram one.
Cool with that part of the lab. Okay. When you get to like 7 and 9, all I'm asking for is increase or decrease. Okay, you can't actually calculate the values because of the fact that you don't know what the values are going to be. All right? So if you look like on number 9, what would have happened if there had been friction where the pulley would not have been able to spin freely? So this is a situation where you start with one thing and you cascade that idea all the way down, okay? So let's say that there had been, it was a rusty pulley, right? You might even run into a situation where if I just put that tiny 10-gram mass on there, if there was enough friction, you might not get any acceleration at all because of the fact that frictional force might be holding it in place. And again, just because you apply a tension doesn't mean that you're going to get an acceleration, okay? So just like if I apply a force to this computer, it doesn't necessarily mean that it accelerates. So just because you apply a torque doesn't mean that you get an acceleration. Just like if you don't apply a force, doesn't mean that you're necessarily going to get an angular acceleration. So this is kind of the visual that you want to have. So we'll need this later on anyway. So
One big all increase.
okay. So if you look at what's going to happen, so this is going to go like this. So if I just let go of it, you get an idea of what that acceleration is. Now, if there's friction, like I'm rubbing my hand against that wheel, what happens to the linear accelerations of the objects?
Decrease.
Becomes less, okay? So this is where you want to say, okay, if there's friction, and you take this through to its logical conclusion. All right, so your linear acceleration is going to be bigger or smaller if there's friction?
Smaller.
Smaller. Okay.
So your average acceleration should be smaller.
Yeah, so if that's the case, go back to the very beginning. So if there's friction, if you look at how you calculated your linear acceleration, that was 2x over t squared. So if there's friction, what's going to happen to the time?
Oh, it'll increase.
It'll increase, right? Because it's going to take longer for it to fall. Okay, it's still going to fall at the same distance, so if the time is bigger, what's going to happen to the value of A?
Decrease.
It's going to become less. Oh, okay. Then follow it through to the next step. Oh, okay. How did you calculate tension? Well, tension is m times the quantity g minus a. You're not going to change g. That's 9.8 meters per second squared. So, okay, a has become a smaller number. Okay, what's that going to do to the tension? Then what's that going to do to the torque? What's that going to do to your angular acceleration? And eventually your moment of inertia. Now, think this through. Just conceptualize this. Leave friction out of the mix. Let's say that the lab that we did had these really, really lightweight pulleys, okay, made out of plastic. They're very, very low density. They don't weigh much at all. But imagine if we did the same lab with those pulleys made out of steel, okay? The exact same pulleys, but they're made out of steel. What would happen to the moment of inertia? It would increase because you'd have a lot more mass, right?
Yeah.
So if you had a lot more, same size pulley, imagine that you have another pulley right here made out of dense iron. Your moment of inertia would become a bigger value. Well, that's then, if you want to start with that idea, okay, then how's that going to play out? What's that going to do to the acceleration of the falling mass? What's that going to do to the tension? What's that going to do to your angular acceleration? What's that going to do to the torque? Okay? So that's where you want to be able to take an idea and go, oh, how does that cascade all the way through? Okay. So on number 9, you should have a blend of increase and decrease. You should have some or both. None of them are going to be no change. Okay. On number 10, because if number 10 starts wrong, everything's going to be wrong. So your answer to 10A, that angular acceleration, should be around your little bit less than your age right now. On 10D, where it asks for how many revolutions, it asks for how many revolutions, not radians, revolutions. That answer on 10D should be around 30,
Okay, yeah, close enough.
okay? And at the end of the day, when you get to G, what is the angular momentum of the tire at the 4.75 seconds? That should be around 70,
Yeah. Who else? Please.
okay? So that should kind of
Interesting.
give you some idea on how that's gonna play out. Okay,
So,
let's talk
would you say
about,
170 is close or not close? 206.
not even by government standards is that an acceptable error.
Cool, I got 206.
You got what?
Six.
You got 206?
Maybe.
What's your answer for E?
2.6.
Oh, there's your problem.
Wait. What if you got 0.943? Is that
That's
okay?
cool.
Okay.
Oh, that means
So that means my velocity's wrong.
What do you have for C?
76.5.
Yeah, it's
Whoa.
6.5.
Whoa.
What are you messing up?
Okay, no, I literally, for some ungodly reason, have the angular velocity of the tire is 76.5, and then down here, what is the angular momentum of the tire at the end of the day? Right? I butt 0.943 kilograms per meter squared times 181.6. I don't even know where that came from. Oh, that's the number of radians.
That's not.
is not
that's
it.
true.
whoa.
Never mind. I know what I did. I found my error.
I'm still looking for mine. I did something.
That's an easy fix,
I
though.
did something and
Yeah, that was bad.
I just have to be less
Bad.
clown.
Bad.
Inertia of the tires.
Okay.
So
I was like,
cylinder.
I've got all of the answers right. I'm not sure how I messed up the last one.
Okay, so let's talk about the first multiple choice question. So on this one, you don't have to calculate the
I
moment of
forgot
inertia.
to square a number. That's why.
You know what that is? That's 2 kilograms meters squared. Okay? There's nothing to calculate. Boom, there it is.
DP.
You really don't need it, but that's not the point. So, rod begins rotating from rest, accelerating, rotational velocity is 4 pi radians. So here's the story. So, don't be afraid to analyze problems using like different ways to view this. So, even though you're not asked to, you could draw this on an omega time graph,
But T.
okay? A butt time graph.
But time.
Where's it gonna start?
0, 0.
0. And it's gonna go up like this, okay? What would the slope of that line represent?
Angular acceleration.
Your angular acceleration, right? What would the area underneath it represent?
Radians.
Radians,
Yes!
okay?
That was a guess.
Just like if it was a velocity time graph,
That makes sense.
that would be displacement in meters. If since it's radians per second times seconds, the seconds are gonna cancel out, you're gonna get
Radians.
radians. Okay? Boom, there you go. Now, so just like you have all your linear equations,
Greg, you might want to move that pulley. It's right in the middle of your screen. I just realized that. For Colin's sake. You're welcome, Colin. Don't say I never did anything for you.
so just like you could have v squared equal to v naught squared plus 2ab, guess what? You can have omega squared equals but not squared, which is just fun to say, times 2 theta times alpha. Okay? You can have v equals v naught plus at, but equals but naught plus alpha time. Any time you have a linear equation, you can write the exact same thing with angular. Okay? All you have to do is replace the variables. So make sure by tomorrow you know that theta is distance, omega is velocity, alpha is a. Okay?
And I mean, they are on our.
I know.
Handy
I'm
dandy.
just telling you.
Oh, are they?
Yeah. They're on the
Now-
right side.
So if you look, you want the acceleration, so you're basically trying to find the slope of that line. Now, they don't give you time. If they did, that would be a simpler way to do this. But they do tell you that it moved through 2 revolutions. So since it moves through 2 revolutions, can you keep the revolutions?
No.
What do you want to change those into?
Radians.
Radians. So then you can go, oh, okay, now I have my radian value. What's the initial velocity?
0.
0. Do you know the final velocity?
4 pi radians per second.
You got that number. What's the only number you don't have?
Fish.
Fish.
What's the only number? Fish.
No.
Number 5.
Anyway.
It's fun too.
Now this is kind of weird because this is the pure mathematical answer because I left it all in terms of pi, but it simplifies down nicely. Now on number 9, so let me kind of give you a visual on number 9. So imagine that I've got Polly the penguin. Okay, so let's say this is 1m, okay, and I got Polly the penguin on one end, and then I've got 2 m's out here on the end. Now, what's cool about this one is that you're not rotating about the middle. You're told that it's going to rotate about point X. So here's your setup. I got Polly the penguin here, and then I've got these out here on the end, okay? So, let me give you a hint. Just focus on each one individually. So if this is the case, if you were just to find the moment of inertia of m,
No, you're right.
what are the, because you're treating it as a point mass, how would you just find the moment of inertia of m? Do not make this difficult.
Point mass.
Wait.
mr squared.
Yeah.
mr squared, what's your mass?
M.
What's the distance?
X. 3x. Or X.
No,
X.
no,
X.
no.
X.
It's just x. So the moment of inertia of that m is just mx squared.
Oops.
Oh,
Because it's based upon where it rotates. Okay? It isn't based upon where it is from the other one. It's based upon where it is from the point of rotation. So now, look at this. Now I need to find the moment of inertia of this end. What's that going to be?
MX. Well,
2m.
2m.
2x squared.
Times
4x.
4x squared, right? Because 2x
Well,
2x squared
2x squared in parentheses.
is. Wait. Yeah. Yes.
Yeah.
Now, since
means
they're
I need
both
to
going in the
recalculate.
same direction, are the moments of inertia basically helping each other out?
Yes. So you add
Yes.
them.
Add them together. Cool with that one.
wait, so is it
Wait.
No.
No. Not cool. Because all of that is squared. So it should be.
Yeah.
Yeah, 4mx
I don't
squared
know.
plus x squared is 5mx squared. 4 plus 1 is 5, I think.
What did you get on the very last?
I had to ask my dad for help on the last one.
What did you get?
D.
D?
You're given. You're already
I got nowhere
given
near that.
I. Or it's
I did this with my dad.
What does your
Well,
dad do for a living?
He's an engineer.
Okay, so
He's an
that's
aerospace
So we
engineer.
might-
So I
So
think
he's probably right. And WordCamp did say it takes a lot of work. So
yeah. You have like 3 lines.
Yeah, I have
don't
3
think
This
that's
is
right.
what I have.
yeah, I have 3 lines. That's
Yeah.
definitely not it.
Hey, Will's
with my dad's help, I was able to do it in this.
Okay.
Will's amount of
The
work.
re- all of this on here, that's me trying to figure it out by myself and failing.
Sometimes that's how you learn.
It's definitely not A1 minus A2.
It's definitely not what?
The angular acceleration of M1 minus the angular acceleration of M2.
No. Okay,
Go to jail.
if
What did
you
it say?
start this
What did it
problem
say?
wrong, everything is going to be wrong, okay? So I wanna make sure everybody's cool how you can solve this. And again, you are not gonna have to go through all of this solving it on the test tomorrow. But you need to understand how this problem works, okay? So if you start with M1, and you have to establish this, which direction does M1 move? Up or down?
Down.
Down. So what is bigger, the weight of M1 or the tension?
Oh,
Wait.
Wait.
When
So if you
tension's
take
bigger, it goes up.
M1G, which is gonna be the bigger number, and no, we're not making none of, any of this negative gap, Sean, minus tension 1, will that equal your net force? Yes, which is gonna be M1A. But none of this has to do with linear stuff, it's all angular. So how are you gonna rewrite this? M1 times, or A equals
Our fish.
R fish.
Oh, I can't believe I got that right.
Right? And I'm gonna use R, not 2R, I'm gonna use R.
What do you mean, Cohen? We did this in
Go
class.
with this. Okay?
This is the part he showed us in class.
Yeah, but I lost my pencil for this part, so I was.
Oh.
It was
Oh
gone.
my God, I've lost my.
Remember how I was looking around for my pencil, and my calculator,
Oh yeah.
desperately?
I do remember that.
Okay, now,
This was why.
I need to get tension by itself. So I hate negative numbers, so I'm gonna add that over here and subtract that over. So I'm gonna have tension 1 equal M1G minus M1R alpha. Okay? Go with how I did that. Simple algebra. So I've got a common factor of M1 and R. So if you wanted to, you could factor out,
M1.
you could factor out M1, I'm sorry. So
T1 equals M1 times G minus R fish.
okay?
Yep.
Now, are the units gonna be the
IR
same
fish.
on everything that you're gonna try and subtract?
no.
They have to be. What's G in?
Meters per second squared.
Meters per second squared.
Oh,
What's
fish.
R in?
Meters.
Liters. What's alpha in?
Radians per second squared.
So you get meters per second squared minus.
Meters per second squared.
If you don't, guess what? The equation fails at this point.
Yay!
Okay. Now,
My favorite.
over here, which one's bigger? Tension or M2?
Tangent.
Tension, because that's the direction that it goes. So I'm going to take tension 2 minus M2G equals M2. Now this gets a little bit tricky because now I've got to use 2R alpha because of the fact that that radius that's making that spin is 2R. It's not R, it's 2R. So now when I do this, I've got tension 2. This is a little bit easier algebraically. So then I've got M2 times 2R alpha plus M2G. And again, if you wanted to, you could factor out an M2 and get 2R alpha plus G. Again, would the units work out?
Yes.
Yes. If they don't,
The equation
Bad
fails.
things happen.
Bad and dumb.
now,
Very bad and dumb.
here's your visual. You have two competing torques. Hold on, let me rewind.
Give us a moment for technical difficulties.
Yeah. we had a failure on the set.
Caused by Cohen.
Yep,
It's
I looked
Cohen's
at it
fault.
funny.
It's Cohen's fault.
And, uh,
You know, I didn't even check to make sure that that was closed.
Yeah, if it was open, you'll be redoing this assignment.
Bad and dumb.
Don't worry, I'll just copy what I got.
Cohen's bad and dumb.
I'm ready for C.
I'm not doing too hot in this class right now. I have like an 88 or something.
That's where I'm at right
On a
now.
retest, then I got mine.
Up from an 84
That's
like
better
2
than
weeks ago.
Oh yeah, way better. Oh, about
Yeah, I think I got mine
4 times better.
Oh yeah.
I need to retake this.
For this one, wouldn't it be?
I'm in a 4.
Wouldn't it just be D? Because you have to.
I knew it was
Because you have a 2n.
I knew
This
about
is
it.
a 2x squared.
Yeah.
So that's 4.
Okay, here we go. Now that
Add
we've
another
reset
mx
this,
squared.
thank you very
That's
much.
9.
So, you have two competing torques. The smaller torque, if from your perspective, is trying to make this
You're right.
wheel
We want to
spin
make sure.
clockwise.
We tell Gipshawn.
The outer torque is trying to make it spin
Yeah,
counterclockwise. So, now, what if the two torques were exactly equal? What would happen?
Gipshawn did a bad and dumb.
What's it's not 9.
If the two torques were exactly equal, what would happen?
It would stay in equilibrium.
It would stay in equilibrium, nothing's gonna happen. So by virtue of the fact that when I let go of it, it begins to accelerate, that tells me that I have an imbalanced torque. Okay, so, let me hook this back up.
Wait, it's on
Yeah, you got it first.
I had it right the first time. I just did it weird. I
Okay,
did it weird and wrong. And still got the right answer.
weird and wrong.
And somehow still got the right answer.
Okay.
Weird and wrong.
It was. Yeah, war is bad. Weird and
Square the
wrong is
2 as
bad
well.
and dumb. It was really weird.
Okay. So, would you agree that the difference between the two torques is gonna equal your net torque, which is also gonna equal I alpha?
Yeah.
Cool with that?
So
Yep.
True?
See.
Now, why did I subtract T1 minus T2? That is not tension, that's torque.
Torque.
use the other T then. I started writing
net
stuff down.
torque.
Because it's net torque. And torque 1 is bigger than,
Torque 2.
that's why I wrote it that way. Now, at the end of the day, how do you calculate torque?
The tension times R.
Radius, right? So on that tension one, I'm going to write R times, which is going to be that radius. And then you can either do the factored out version or whatever. It's M1G minus MR alpha. Okay? Cool with that.
Yeah.
All I did was take the radius times the value of how you can calculate the tension.
Is it easier to work with factored out?
It really, you kind of have to look at where your multiple choice answers are, because you got to distribute and recombine everything anyway.
Yeah, good
Yeah.
point. I'll just unfactor that real quick.
So then
I
you
like
got
mine
minus
factored.
2R, okay? Because now I've got to use that outer radius of 2R. And then that's going to be times M2 2R alpha plus M2G. And that all of that equals I alpha. So now, at this point, now you have to figure out, ooh, what are my multiple choice answers? So what I did at this point, I distributed that R, and then I distributed, now you have to be careful because you're distributing a negative 2R,
Yeah.
okay? You're distributing a negative 2R. Then, once you get that, then you can kind of begin to play the, hey, let's combine terms and factor stuff out game. Okay? But this is the heart and soul of what you got to be able to do. Then you just have to look at, okay, well, what are my option in terms of how you want alpha? Because that, at the end of the day, you gotta get alpha by itself. So, like I said, on the test, I am not going to expect you to derive this whole thing. I'm going to expect you to be able to realize, hey, how can I derive the formula for the tension? Okay? Which tension, is the tension bigger or is the gravitational force bigger? And then use that to express the two values of torque. If you can get to that point, that's as far as I'm going to expect you to go on the test. Okay? Not the whole drive thing. Does that make sense?
So that step.
Yeah. If you can get to that step, that's all the farther you're going to have to be able to go on the test tomorrow. Okay? Cool. If you want to hold on to that lab and hand it in tomorrow, you can. If you're cool and you're done, you want to hand it in, that works too. Okay? Any other questions on the lab? Once, twice sold, stop you on the camera.
So you're cold.